Hello everyone, this is Team Swatch, and today we will present you our approach of the Kaggle competition, Real or Not, Natural Language Processing with Disaster Tweets. So here's the plan of our presentation. First we'll talk about data treatment, then the methodology we used, then we will show you our results and our conclusion. So now we are on our notebook. Our goal in this competition was to give the most accurate prediction whether tweets about disasters were real or not. This is a typical binary classification problem for textual data. So we will need to create accurate machine learning models and find the one that gives us the best predictions. The main measures we will use is the F1 score, as it's a mix between precision and recall measures. In this competition, we were given two data sets, a train set and a test set for our prediction. After loading the different libraries we will use in this notebook, we begin exploring the data set. So, exploring the data set, we see that the train set contains 5 columns: the entry number, the ID, keyword, the location, the actual text of the tweet, and the target. The target is binary. 0 means that it's not a real disaster, and 1 that is actually a real disaster. We will train our different models on these data and then we will test them on the test set. As we can see, there are more fake tweets than real ones. So the fake tweets are in blue and the real ones in orange. The test set doesn't contain any target column, as it is what we are to predict. So let's now see how we handle the data. We started by cleaning. The tweets contain a lot of information that are not relevant for our predictions, such as URLs, tag, emoji, number, punctuation, and stop words. So we created a clean function that removes all these useless elements and applied it to both the test and the train set. We will see later on that we didn't always use the cleaned dataset, as it didn't improve our prediction scores. After cleaning, we vectorized the data. So as our datasets are composed of tweets, which are text data, we cannot process them as they are. In order to classify them, we must first vectorize them. Vectorizing the tweets will allow us to perform mathematical operation on them, just like on any numerical data, and thus compare the tweets to classify them. Of course, for the classification to work, both the train and the test set need to be vectorized. So we use TF-Hub and TF-ID. TF-Hub, TensorFlow Hub Universal Sentence Encoder, and TF-ID, Term Frequency, Inverse Document Frequency, are two different algorithms that will compute our text data to vectors before sending it to the classifier models. Moving on to our methodology. Our approach to this problem was to test classifiers with multiple parameters in order to find the best possible results. To implement our strategy, we created 4 different pipelines: TF-Hub without cleaning, TF-Hub with cleaning, TF-IDF without cleaning, and TF-IDF with cleaning. Then we tried to fine-tune the hyperparameters and create a model combining different simple and assembled classifiers. And finally, we experimented both. But how does a pipeline actually work? So a pipeline generally works like this. There is the pre-process phase. The raw data is pre-processed. In our case, the tweets are vectorized using either TF-Hub or TF-IDF algorithms. Then there is the split phase. Generally, the data is split into train, test, and validation sets. But in our case, the split is already done, so we can skip this step. Moving on to the auto-tune phase, the pipeline will find the parameters that return the best results using a given model. In the training phase, the final model is trained with the best parameters on all the data. Then we test our model, so we get the metrics and predictions on the test data. Going back to our notebook, you can see the different classifiers that we used in the 4 pipelines. So we use naive Bayes classifiers, support vector machine classifiers, linear models, other classifiers such as k-neighbors and decision tree, and assemble classifiers such as random forest, gradient boosting, and voting. Here you can see the pipelines in use. So we first define the different classifiers that are going to be used. And then we create pipelines for each version. So the TF-IDF with and without cleaning, and the TF-hub with and without cleaning. And then you can see the results for each classifiers with the F1 score showed here and the classifier used. The same goes for every pipeline. So here you can see the general pipeline results. So keep in mind that these are all simple models without hyperparameters optimization, and that the graphs are shown here for predicting one. So for predicting if the tweets are actually real or not, and not if they are fake. So you can see that for the TF-IDF algorithm without cleaning, the best classifier was SGDC, the same as with cleaning, and both gave us results of 0.72. Here are the results with the TF-hub algorithm, again with and without cleaning, and you can see that we got almost exactly the same score, and the best score was with the SVC classifier. So we notice that we always have better results for predicting 0, so not what is shown on this graph, and we always have better accuracy using the TF-hub algorithm. We also notice that SGDC and SVC are the classifiers that give us the best results, and that using it with TF-hub predicting for 0, we got more than 0.8 accuracy. We also notice that cleaning doesn't change that much the results. Knowing this, we tried to create an all-in-one model with 2 good rated classifiers, SGDC and SVC, for predicting target equal 1 and target equal 0. We used a voting classifier to combine SGDC and SVC classifier. Using such an approach requires fine-tuning parameters and weight, but it gives us better accuracy score. With the voting classifier with TF-hub and no cleaning, we obtained an accuracy of 0.833. So moving on to the BERT classifier. BERT classifier stands for bidirectional encoder representation from transformers. It is a technique for natural language processing pre-training developed by Google. It requires specific vectorization that is not compatible with the 2 previously used algorithms. BERT demands a lot of computing power in order to run and requires fine-tuning of the different hyperparameters, but it is the classifier that gave us our best results. So in this table, you see our best submits to the competition. You can see the classifier used, whether the data was cleaned or not. Actually, you can see that our 4 best results were without cleaning, the vectorization algorithm, and the corresponding score. To conclude this presentation, out of the 10 classifiers used for the pipelines, SGDC was almost always the best ranked. We saw that cleaning didn't change much to the result, and as we noticed earlier, our best scores were performed without cleaning. The TF-Hub algorithm had almost always better results than TF-IDF, and we noticed that the computing power makes a huge difference. For the story, we had to let Bert do his job for more than 12 hours on a Google server. So that's it for this presentation. I hope you got something interesting out of it, and the whole team Swatch thanks you for your attention if you made it this far.